Hi guys, in this video I cover the concept of recursion. Now recursion means that we describe a term and we use the term itself in its definition. That means typically whatever we are describing consists of smaller instances of itself. Now an example for recursion is a file explorer that has folders and each folder consists of files or a folder itself. Then that folder again consists of files or folders. Or a list. A list can be empty, a number, or a number, comma, a list. So here we also have a recursive definition where a list can consist of a smaller list of itself. And then that list again can be empty, a number, or a number, comma, a list. In math, we have the example of factorial. So factorial n equals n times n minus 1 factorial. So again, we have the factorial concept here, the very concept that we are describing. Factorial 3 would be 3 times factorial 2. Factorial 2 is 2 times 1. Factorial 5 is 5 times factorial 4. And factorial 4 is 4 times factorial 3. And so we can expand this out until we hit a certain condition where this ends. And factorial ends at 1. So what is recursion in computer science? There are two places where recursion exists in computer science. The first one is to solve problems when we're defining solutions, algorithms to solve those problems. And the problem consists of smaller instances of itself. The other part is when we define data structures. The data structure that we're defining consists of instances of itself. Think about a class that you're defining and a field, a member variable of that class, consists of an instance of itself. So we have recursive algorithms and we have recursive data structures. So let's go over an example. Let's say we want to sum up the values from 1 to n. In this case, first we start out with iteration. So iteration typically uses loops, for, do, while, for each loop, or iterators. And here I have a variable named sum. Then I have a for loop to generate the numbers from 1 to n using a counter variable I. And I sum up all the values in that variable sum. Now, how can we solve this with recursion? We use a method. I name this sum. I pass an n. And the result of the method would be the sum of all the values all the way up to n. Then I have a condition. If n is less than or equal to 1, I return 1. Otherwise, I return n plus the sum of n minus 1. And note that sum here is the recursive function call. In the definition here, in the function definition, I call the very function that I'm describing. Now, since I pass an n minus 1, eventually I hit the condition and I return 1. So n is basically the counter as I use I in the iteration here. But in the recursive case, I count down from n all the way down to 1. Versus using iteration, I count up from I equals 1 all the way to n. So what do we need when using recursion? We need a function that calls itself recursively inside. And inside the function, we need a base case that defines when we want to stop and a recursive case that is the function call itself. Now, what happens if we don't have a base case or if we forgot to write a base case? So the base case essentially is like a condition in a loop. If we don't have the base case, the function calls itself indefinitely. So if we don't have a condition in a loop, the loop would run forever. Now there's a small difference if we don't have a base case, because using recursion, we always make a function call in each iteration in quotes. So eventually we would run out of memory. since we have a stack overflow. So each function call that we make, we push a stack frame onto the stack. So how can we implement factorial n? So we have a function, factorial, I pass in n, and then we need a base case, the condition when to stop, and a recursive case. So base case, we have a condition and then return statement. And what should be in the condition? When do we want to stop for factorial? So when n is less than or equal 1, I just return 1. And for the recursive case, I do n times factorial n minus 1. It's very important that in the recursive case that I do n minus 1. N minus 1 is essentially the counter. If I do factorial n, I would loop forever. I would never reach the base case. So it's important that I decrement 1 here, or that I subtract 1 from n when I pass the variable into that function call. So the n minus 1 essentially is the counter that I do at the end of the loop when I use iteration. So it's very important that we have the base case and that we do a counter to eventually reach that base case. Now let's take a look. Let's say when I call this function factorial 4 calls factorial 3 because it does n minus 1. Factorial 3 calls factorial 2. Again, n is 3 and 3 minus 1 is 2. And then we hit factorial 1. And factorial 1 hits the base case, right? If n equals or is less than or equal to 1, we return 1. So here we return 1. This returns 2 times 1. This returns 3 times 2. And this returns 4 times 6. So factorial 4 would give us 24. These are the function calls that happen all the way down to the base case. And then at the return statement, we multiply it up and return the final value. Let's take a look at another example, the Fibonacci numbers. So Fibonacci numbers are defined as 0 and 1. Those are the two starting values. And all subsequent values are defined as the sum of the previous two values. So at the bottom, you see the Fibonacci sequence. 0 and 1 are the starting numbers. And then the following number 1 is defined as 1 plus 0. The next one, 2, is defined as 1 plus 1. Then if I sum up 1 plus 2, I get 3. 2 plus 3, I get 5. 3 plus 5 equals 8, and so on. So I always sum up two values. How can we write this using recursion? So again, we need a base case to start with. Here, the base case, I have if n is 0, I return 0, and if n is 1, I return 1. I can simplify this by writing if n is 0 or n is 1, I just return n. So that when I pass in 0, I return 0. When I pass it 1, I return 1. And then the recursive case, I call the function twice. Once with n minus 1 and once with n minus 2. And I add both of them up. That comes from the very definition. Remember, the definition had starting values 0 and 1. This is defined in the base case. And then every other number is defined as the Fibonacci sequence of n minus 1 plus n minus 2. So what is the problem here? It works. It's very easy to write because it comes so natural from the description itself. But the problem is that we do two recursive function calls. We do n minus 1 and n minus 2. And n minus 1, again, we'll call n minus 1 plus n minus 2. So if we just trace this function call all the way down, we would reach n minus 2, which is already computed over here. So we really compute results over and over again. So what you want to really watch out to, that you don't have multiple recursive function calls. You can use recursion if there's a single recursive call, but if you have multiple calls, be very aware that this is likely the situation that you end up with. So to recap, we have iteration using loops, do, while, for loop, for each loop or iterators. And then on the other side, we have recursion using function calls, a base case, and a recursive case. I hope you enjoyed this video. Thank you for watching.